So in this lecture, I will discuss the weak law of large numbers. It's a very nice lecture. I hope you will enjoy it. So remember that we already proved that if we have a sequence x1, x2 of IID random variables such that, well, it has first moment x1, which I will call mu, and then it has a finite second moment, so x1 square finite, then we proved that x1 plus xn divided by n converge in probability and also in L2 to mu. So that we proved already, but we proved it under the strong assumption that you have a finite second moment. So the theorem, the first theorem of this lecture, states that, well, this statement holds only assuming that the first moment is finite. So let's consider a sequence x1, x2 of IID random variables. Let's assume that the first moment is finite, so the expectation of the modulus of x1 is finite. Let's call mu the expectation of x1. And what I claim is that x1 plus xn divided by n converge in probability to the expectation of x1, which is mu. So this is the first main theorem of this lecture, and I will provide two different proofs of this fact. So here is a first proof. What we will do is that we will truncate these random variables xi. So I will fix a real number a which is positive, large, and I will introduce a new sequence of random variables which I will represent by yj. Actually, it depends on a. So sometimes I will write yj with a to stress that yj depends on a. And this is just the random variable xj, but truncated at the level a, which means that yj is equal to xj, provided that xj is less or equal than a. In other words, yj of a it's equal to xj if xj is less or equal than a, otherwise it's 0. So I have two observations about yj. The first one is that, well, yj it's bounded by a. That's clear from the definition. And then that yj is a sequence of IID random variables. And that we have seen because yj is a function of xj. Since the xj are independent, the yj are independent, and they have the same law by definition of yj. So yj it's a sequence of IID random variables which are bounded by a, and therefore by the theorem I mentioned, y1a plus yna divided by n converge to the expectation of y1a, and I will represent that by mu ay. So mu ay will be the expectation of y1a, and this is the expectation by definition of y1. This is the expectation of x1 truncated at the level a. So that we know by the previous result. And now let me define ZA. Well, ZA will be the difference between xj and yj. So ZJA will be equal to xj minus yja. So this means, by definition of yj, that zja it's equal to, well, by definition of yj, zja will be equal to 0 if xj it's less or equal than a, and it will be equal to xj otherwise. And from this relation, of course, we get that xj it's equal to yja plus zja. So from this decomposition, we will deduce the law of large number for the sequence x from the one of yj, saying that, well, if a is very large, then the average of zj it's very small. So we introduce these variables yja, which are the variables xj truncated, and zj by this identity. So let me define as, well, I already introduced mu ay as the expectation of y1a, and mu az will be the expectation of z1a, and this, by definition, it's equal to the expectation of x1, well, condition, well, x1 multiplied by the fact that x1 it's larger than a. Remember that chi is the indicator function of the set, so this is equal to 0 if x1 is smaller or equal than a, and it's equal to 1 if x1 is larger than a. Well, what we know and what I will I will use later is that, well, take the absolute value of mu az. So this is equal to the absolute value of this expectation, and this is bounded by the expectation of the absolute value of this expression, which is the expectation of x1 multiplied by the indicator function that x1 is larger than a. And you see, since by assumption x1 has a finite first moment, this means that this random variable has a finite expectation. This expression is converging to 0 as a converges to plus infinity, so the measure of this set is converging to 0 as a converges to plus infinity. Let me just prove that. So what I'm saying is that the probability of this set it's converging to 0 as a converges to plus infinity. And this, well, for instance, follows from Chebychev inequality because this is bounded by 1 over a times the expectation of the absolute value of x1. This is finite. As a converges to plus infinity, this converges to 0, as I claimed. Therefore, this is a set whose probability, whose measure converges to 0. Since x1 has finite expectation, this is converging to 0 as a converge to plus infinity. So we used already this fact. I will give you in the notes a reference for this statement, but what we get from that is that as a converges to plus infinity, mu a0 converges to 0. So now we are ready to prove the law of large number for x1, xn. What we want to estimate is the probability that x1 plus xn divided by n minus mu it's larger than epsilon. So we have to show that for every positive epsilon, this probability converges to 0. So we need to estimate this probability. Well, let's use this decomposition of x to write this sum as two sums. The first one, it's y1 plus yn divided by n. Note that I'm not writing the superscript a, but a it's assumed, plus z1 plus zn divided by n, minus n mu, which is the expectation of x1. I will write this expectation as the expectation of y plus the expectation of z. So we represented by mu a y, the expectation of y, mu a z. So this is minus mu a y minus mu a z. And I'm asking, well, that this expression to be larger than epsilon. So I just use the definition of y and z to rewrite this probability as this one. Now, I have two terms. So the average of y minus mu y is 1. The average of z minus mu z is the second term. I'm saying, well, if this is larger than epsilon, then one of the two is larger than epsilon over 2. So this is bounded by the probability that y1 plus yn divided by n minus mu ay it's larger than epsilon over 2 plus the probability that z1 plus zn divided by n minus mu az it's larger than epsilon over 2. And well, maybe let's now recall that we have a in both terms. Right? So this is clear. Now we have seen that if I send n to infinity, this first term converges to 0 for all a. So I fix a positive a, and the limit for that fixed a, the limit as n goes to infinity of this expression is 0, because we have seen that a law of large number, a weak holds for the average of y, because this is a sequence of IID random variables which is bounded by a. So these terms converge to 0. So now we need to estimate the second one, and the second one I will use the Chebychev inequality to say that this term it's bounded by 2 divided by epsilon times the expectation of this expression Now let's estimate this expectation. Well, this absolute value, it's bounded by the absolute value of the first term plus the second one. So this is bounded by 2 divided by epsilon times the absolute value of mu a z plus the expectation of this average, but this it's bounded by the sum 1 over n, the sum from 1 to n of the expectation of zj. Let me write a to recall that depends on a. Since the random variables zj are identically distributed, this average, it's, well, this expression does not depend on j. So this is actually equal to 2 times 2 divided by epsilon times mu a z plus the expectation of z1 a. And therefore, what we have proved so far is that this expression is bounded by that one. You see that this expression does not depend on n. So if I take the limit sup as n goes to infinity, this first expression converges to 0, and this one is bounded by that, so that this is bounded by 2 divided by epsilon. And now let's recall what is mu a. Mu a, well, we have this bound. It's bounded by this expression, and z1, it's exactly what's written here. So we have that this sum, it's actually bounded by 2 times this expression. So I have here a 4, and the expectation of x1 chi x1 larger than a. So what we proved so far is that the limit sup of this probability, it's bounded by 4 divided by epsilon times this expectation. And we have seen, I mentioned this result before, that this expectation converges to 0 as a tends to infinity. And this proves the law of large numbers for the sequence x, because we already proved that this limit, the left-hand side does not depend on a, so we can send a to infinity to get that the right-hand side converges to 0 as a goes to infinity. So this proves, this concludes or completes the first proof of this result. Let me just say that we call this a weak law of large numbers because we are proving this convergence in probability. We will see in a while that instead we would like to replace the convergence in probability by an almost sure convergence. And when we prove that a sequence converges almost surely to something, we will say that we have a strong law of large numbers. So this is a weak because we are proving convergence in probability. Let me give you a second proof of this result. The first proof was based on truncation. The second proof will be based on the characteristic function. So we have seen that if a sequence Zn of random variables converge in distribution to a real number mu, then it converges in probability. So if you want to prove that this sequence converges in probability to mu, it's enough to prove that it converges in distribution to mu. So my goal will be to prove that x1 plus xn divided by n converge in distribution to mu. We have seen that to prove convergence in distribution, it's enough to prove that the characteristic functions of x1 plus xn divided by n t, so let me represent by phi x1 plus xn divided by n the characteristic function of this random variable computed at t, that this converge to mu of t. So if we want to prove this convergence in distribution, we have seen in the previous lecture that it's enough to prove the convergence of the characteristic functions for all t. Well, so this is the random variable which is equal to mu with probability 1. So its characteristic function, it's easy to compute. It's exactly equal to exponential I mu t. So if we want to prove this statement, it's enough to prove that this sequence of functions converge pointwisely to this function. Fine, so let's do that by using the properties of this sequence, so by using the fact that they are IID. So we know that fx1 plus xn divided by n at t, well, that this is equal. We have seen that if you take a random variable and you divide it by a number, to compute the characteristic function of this random variable, it's to take the characteristic function of the random variable and compute it at t divided by n. So this is first property of the characteristic function. Now, these random variables are independent, so the characteristic function of the sum is the product of the characteristic functions. And now, well, these random variables are identically distributed, so this is actually equal to fx1 tn to the power n. Now, we assumed that these variables, or the variable x1, has finite first moments, so that we have an expansion for the characteristic function, which we proved in the previous lecture. So we know that fx1 at some s, it's equal to let me write it exactly as we wrote in the previous lecture. So this is a sum from j from 0 to 1, I s to the power j divided by j factorial, the expectation of x1 j, and then there is an error, and the error is s to the power 1 divided by 1, and a remainder of s, and this remainder has the following property: its absolute value, its norm, it's bounded by 4 times the expectation of x1, and the limit as s goes to 0 of rs, that this is 0. So these are the properties of the remainder. So, well, here the sum goes from 0 to 1, so we can rewrite that. That's, well, when j is equal to 0, this is 1, so this is 1. And now when j is equal to 1, this is is mu, because I'm calling the expectation of x1 mu, so this is is mu, and then you have s times rs. So this is our Taylor expansion of the distribution of the characteristic function of the random variable x1. So let's just replace phi x1 by this expression in this formula to get, so let me erase these lines. So this is equal by what we have seen. So 1 plus, now I'm taking s to be t over n. So this is I t mu divided by n plus s, it's t divided by n, or t divided by n. And this is to the power n. So let me write this as 1 plus I t mu plus t rt divided by n to the power n. And now what I claim, and I will give you a reference for that, is that if we have a sequence of complex numbers zn converging to a complex number z, then 1 plus zn divided by n to the power n converge to the exponential z. Now if we look at this expression, this is exactly what we have, where zn, it's the numerator of this fraction. And the numerator of this fraction, by the second property of R, for any fixed t, this is converging to it mu. So if I call this expression Zn, since Rs is converging to 0 as s goes to 0, this expression, in this expression Zn, it's converging to it mu. And therefore, by this property, this expression, it's converging to the exponential of z, but z it's it mu. So we proved that indeed the characteristic function of the average of dx at point t converge to exponential it mu, which is, as we have seen, the characteristic function of a random variable concentrated at mu computed at t. And therefore, the average of x indeed converge to mu in distribution, and therefore converge to mu in probability, as we claimed. So it's a very simple proof relying on the characteristic functions. So we presented 2 proofs of the weak law of large number. Remember, weak means that we have convergence in probability. And now I want to consider the same result, but replacing P, the convergence in probability, by an almost sure convergence. So I would like to prove that the average of the random variables x converge almost surely to mu. Actually, we have seen that if we assume that this sequence is a sequence of IID and that the fourth moment is finite, then this result follows from the Borel-Cantelli lemma. So in order to prove this statement, we will need two bounds, two inequalities, which we will present in this lecture, and in the next lecture, using these two inequalities, we will start proving that this convergence holds almost surely. So let me consider a sequence of random variable x1, x2, x3, which are independent. So I'm not assuming anymore that they are identically distributed. And let me define Sn to be the sum of the first n variables. So what we want to investigate is the probability that the maximum, we want a bound on the maximum of these variables, that the maximum of Sj, j from 1 up to n, it's larger or equal than A. So we will present two bounds for this probability, and what you want to understand these random variables as a random walk. So let me say that here you have time, and the time is discrete. So you started at time 0, here is time 1, time 2, time 3, and so on. And you represent in this picture Sn. So here is the value of x1. So you jump from 0 to x1. Then you add to, so this is S1, which is x1. Then you jump to S2, which is x1 plus x2, which means that x2 is equal to this height, and so on. And what you would like to estimate is the probability that this walk attains a height A. So here is A, here is minus A, before time n. So you have fixed a time n. I'm understanding these indices as time, and I would like to estimate what is the probability that your random walk hits the level 8 or the height 8 before time n. So what would we get if estimating just by Chebychev without the maximum? So let me assume that now that these random variables have mean 0. And let me assume that they have a finite second moment. And let's represent this second moment by sigma j square. So what would be the estimate we get for this probability if we use Chebychev inequality? By Chebychev inequality, this is bounded by 1 over a square, the expectation of Sn square. Now this is equal to 1 over a square. Sn is the sum of the first n random variables. Now expand this square. You have the cross terms, but since the variables are independent and the expectation are 0, the expectation of the cross terms are all 0, because expectation xi, xj is the expectation of xi times the expectation of xj, and both are equal to 0. So only the diagonal terms will survive. And the expectation of the square of xj, it's what we represented by sigma j square. So this is the bound we get by using Chebychev for the last term. Well, what the first theorem I will prove states is that actually this bound holds for the maximum as well. So what we will prove is that the probability of this maximum to be larger than a, well, this is less or equal than 1 over a squared times this sum, which is quite surprising if you see that this is the bound you get by estimating just the last term of this maximum. But actually we prove that this is the case. So let me state what is known as Kolmogorov inequality. So we have a sequence of independent random variables. We assume that these random variables have mean 0 and finite second moment. I'm representing by sigma j square the second moment of the variables xj. Now let's represent by sk the sum of the first k terms of this sequence. And what we want to prove is that for all a positive and for all n larger than 1, the maximum of Sj j between 1 and n larger than a, it's bounded by 1 over a squared times the sum of sigma j square j running from 1 to n. So here's the proof. Now let me call t the first time at which this sum hits the level a. And here I can put larger or equal. So t is the minimum of k larger than 1 such that sk is larger than a. So the first time at which we hit the level a. So in my picture, we started from 0. Here's time n. And at some point, we reach a level larger than a. So this is a minus a, and this is 0. And this will be my time t. And so saying that the maximum of Sj is larger than a is the same as saying that t is less or equal than n. So what I claim is that the event that the maximum of Sj is larger than a is exactly to say that t is less or equal than n. So what we want to estimate is actually the probability that this random time is less or equal than n. I think this is clear. So the probability of this event, which is what we want to estimate, it's the probability that t is less or equal than n. Well, but if t is less or equal than n, this is the sum from 1 to n of the probability that t is equal to j. And probability that t, what means that t is equal to j? So let me write this event because we will need it later. T equal to j. When is t equal to j? Well, but this corresponds to the fact that, well, S1 it's smaller than a, S2 it's smaller than a, Sj minus 1 it's smaller than a, and Sj it's larger or equal than a. And what's important to see is that this event depends only, so this is a function of x1, xj. Right? to know if t is equal to j, to know if we hit the level a at the first time at time j, I only need to know the values of x1, x2 up to xj. So this event, it's a function of x1, xj. And therefore, this event is independent from the variables xj plus 1, xj plus 2, and so on, because these random variables are independent. Moreover, on the set in which t is equal to j, I know that sj is larger or equal than a. So I can bound this so let me write the expectations of the probability of this event as the expectation of its characteristic function. And now, since I know that on the set t equal to j, sj is larger than a, this means that 1, it's bounded by sj divided by a, or sj squared divided by a squared. So this is what I want to replace here, sj squared, but by a squared. Now, suppose that we are able to show that this is bounded by the same expression, but in which I replace sj by sn. So suppose that we can prove this inequality in where I have the expectation of sn squared divided by a times the characteristic function that t is equal to j. Well, if I can prove this inequality, let's assume for a while that I can prove it, I claim that the proof of this result is completed, because now it's a matter of, well, I have here the sum, I can push it inside the expectation, I have the sum of these indicator functions, but the sum of these indicator functions, since these events are all disjoint, it's equal to the indicator function of the union. So I can replace this sum, I can write this sum as saying that this is equal to the expectation of Sn squared divided by a squared times the characteristic function of the event that t is less or equal than n. But this is clearly bounded by the expectation of Sn squared divided by a squared, and we already computed the expectation of Sn squared, which is given by this sum. So we have 1 over a squared, and therefore the theorem is proved. So all we need to check is that this expectation is indeed bounded by this expectation. If we can do that, then the proof is complete, as I just showed. So I will erase everything, and I will prove now, I'll concentrate on this inequality, which means that I will prove that this expectation is bounded by this one. And of course, I forgot here the a squared. So when I'm proving that, I will just erase a squared, and I'll prove just that the expectation of sj squared times this characteristic function is bounded by the expectation of Sn squared times this characteristic function. So to complete the proof, I need to show that this inequality holds. And here I rewrote the event t equal to j. So t, the first time you hit a, it's at time j. If you are below a at time 1, up to time j minus 1, and then at time j you are above a. So in order to prove this inequality, I will just rewrite. So I take the right-hand side. The right-hand side is Sn, and I will rewrite Sn as Sn minus Sj plus Sj. So you see, Sn minus Sj is how much your random walk jumped between time j and time n, while Sj is its position at time j. So this two events you see are independent. So here is time j, here is time n. The position, so all these events, the event t equal to j and sj, depend on everything which happened before time j. And while Sn minus Sj depends only on what happened after time j. And what I'm saying is that actually this random variable is independent from the random variable Sj and t equal to j. But I will be more precise about that. For the moment, let me just expand the square. So I have one term, which is the expectation of Sn minus Sj square times the indicator t is equal to j. Then I have the cross term plus 2 the expectation of Sn minus Sj times Sj, the indicator that t is equal to j, and then plus the expectation of Sj squared, the indicator that t is equal to j. And what I wish to prove is that this term here, which I wrote here, it's larger than this one. So what I claim that it's enough to show that the cross term is equal to 0. If I show that the cross term is equal to 0, I obtained that the right-hand side is equal to the left-hand side plus a positive term, and therefore this inequality holds. Therefore, the proof reduces in showing that this expectation is equal to 0. And that will follow from the independence. So let's write what is Sn minus Sj. So you see from this definition, as I was saying, Sn minus j is the sum. So is the sum for k going from j plus 1 up to n of xk. So this is Sn minus j. And then I have Sj and the characteristic function that t is equal to j. Now, Sj is the sum up to j. So Sj is a function of the variables x1 up to xj. And the event t equal to j is also a function of x1, xj, as I was explaining before, because in order to know if t is equal to j or not, you just need to know the trajectory, the values of the variables x1 up to xj. Because by knowing them, you know that if s1 is smaller than a, sj minus 1 is smaller than a, and sj is larger than a. So both these variables are functions of x1 up to xj. While this term, it's a function of the variables xk for k going from j plus 1 to n. Since these variables are independent, this expression here is independent from this expression, because we have seen that if we have independent random variables, you take functions of them, then the functions are independent. So this expectation is actually equal to the product of the expectations. And the first one is the sum from k going from j plus 1 up to n of xk times the second expectation. But since the random variables xk have mean 0, this expectation is equal to 0, which means that this expectation is equal to 0, and this is exactly what I claimed before. And as I said, once you know that this is equal to 0, you get this bound, which was what we needed in order to complete the proof of Kolmogorov inequality. And this is the proof. Now let me state a second inequality. This one is due to Levy. So the theorem is as follows. let's consider random variables x1, x2, and so on, which are independent. Note that I'm not assuming that they have mean 0 finite second moment, I'm just assuming that they are independent. And let's assume that you fix A, you fix a positive A, and you assume that there exists a delta positive and less than 1, such that the probability that xj plus xn to be larger or equal than a over 2, that this is bounded by delta for all j between 1 and n. So a is fixed, and you are assuming that there is a delta between 0 and 1, for which this probability is bounded by delta for all j between 1 and n. So you see that here it's concerning to the last terms. The sum of the last terms larger than a over 2, it's small for all j. Then what this inequality claims is that the probability that the maximum between 1 and n of j, of sj, as before, larger than a, that this is bounded by delta divided by 1 minus delta. So before I prove it, let's try to get a feeling about why this is true. And what I claim is the following. Here I'm asking that I want to bound the probability that you hit level A before time n. This is telling you that, well, the contribution of the last terms to be large, it's small. So note that this inequality holds for all j, so it holds also for j equal to 1. So what I want to do is, well, let's take this event, that the maximum of Sj it's larger than A, and consider two events. Well, let's cut it by Sn smaller than A over 2 plus Sn larger than A over 2. Right? Well, when Sn is larger than A over 2, by the assumption, we know that this event has probability smaller than delta. So this expression is small. So it remains to estimate this one. We want to prove that this expression is small. Well, the second term is small. So in order to prove that it's small, we just have to show that this one is small. But now, what is this telling you? Well, this is telling you that in our picture, that here is 0, here is level A over 2, and then we have level A. And this is telling us that, well, at time n, you are somewhere, so this is time n, and at time n, you are between minus A over 2 and A over 2, and this is minus A, this is level A. But the maximum, it's larger than A. So there is a point here in which there is a time in which you hit the level A. If you hit the level A before time n, and at time n you are below A over 2, means that the contribution here, it's at least A over 2. So from j to time n, so Sn minus Sj, for some j, that this should be larger than A over 2. So there exists a j. Of course, the j, it's not known. It depends where this maximum has been attained. But at this random value j, you know that the difference between Sn minus this Sj, it's at least A over 2, because you were above A at this time j, and you are below A over 2 at time n. And this is exactly, and this event, the probability of this event, it's exactly the one you know how to control. So this makes the strategy clear. What you want to do is, well, since you know how the, let me call this random walk behaves at the end of the interval, at last steps of this interval, well, you use this information in order to say that, well, if this maximum, if you hit A and you are below A over 2, this means that you crossed A over 2 in some, well, the Q of your sum, so this expression has to be larger or equal than A over 2. And on the other hand, if you're above A over 2 at time n, well, then you can use your assumption in order to estimate. So what we will do is we will divide this event in two disjoint events. This one we will use the assumption to bound, and this one, well, we have to do some, we have to make precise what I said, because as I pointed out, this time at which you hit level A, it's a random time, so you have to make this random time a deterministic time in order to be able to use this assumption. So let's prove this theorem. I wrote here what we want to prove, and let me again call T the first time such that Sk it's larger than A. And of course, if Sk it's smaller than A for all k, we will just set k to be T to be 2n, but because what I really want to estimate, it's the event that T it's less or equal than n. So I don't care really how to define T if Sk keeps below A for all k. So this event that the maximum of Sj is larger than A, it's equal to the event that T it's less or equal than n. And therefore, what I want is to estimate this probability, and what I propose is to divide that in two pieces. The first piece is that the probability that T it's less than n, and Sn it's below A over 2, plus the probability that T it's less or equal than n, and Sn it's above A over 2. And we will estimate the second term by saying that this is less than the probability that Sn is above A over 2, and by assumption, this is bounded by delta. So the second term, it's bounded by delta. So what we really need to do is to estimate the first term. So the first term, let's decompose it as before, as the sum for k equal to 1 up to n. Actually, okay, so let me write it, probability that T it's equal to k and Sn less than A over 2. You see that T is equal to k means that at time k you're above A, so you can't be below, k can't be n, because you can't be at the same time above A and below A over 2. So I can really take the sum up to n minus 1. So now I need to recall what T equal to k means. I wrote it several times, but let me write it again. T equal to k means that S1 it's smaller than A, Sk minus 1 it's smaller than A, and Sk it's larger or equal than A. And so I can write this as T equal to k. And now I know that Sk it's larger than A in this set. Here I'm imposing that Sn it's less than A02. So it follows from these two inequality that Sn minus Sk, that this is larger than A02, strictly larger, right? If Sk is larger than A and Sn is smaller than A02, then Sn minus Sk has to be larger than A02. So I will bound this sum by the sum from 1 up to n minus 1, t equal to k, and now I'll just require that Sn minus Sk it's larger or equal than A02. And you see that here I replaced the random time t by this deterministic time, which is k. Now Sn minus k is the sum from j from k plus 1 up to n of Sj. And I want to say that these two events are independent, because t equal to k depends only on x1, x2, xk, as I said before. So this is a function of x1 up to xk, while this sum, it's a function from xk plus 1 up to xn. The variables xj are independent, so these two sets are disjoint, and therefore these two variables are independent. So I can write this probability as the product of the probabilities. So this is equal to the sum from 1 up to n minus 1 of the probability that t is equal to k and the probability that the sum from k plus 1 up to n of xj it's larger or equal than A02. Now by assumption with j equal to k plus 1, I know that this probability is bounded by delta. So this is less or equal than delta. And here I have the sum over the probability that t is equal to k. So this is equal to the probability that t is less or equal than n minus 1. And this is bounded by t times the probability that t is less or equal than n. So what did I prove up to now? I proved that the probability that t is less or equal to n, it's bounded by the sum of two terms. The first term, it's bounded by delta times the same probability, and the second term, it's bounded by delta. So let me write this here. I'm saying that we just proved that this probability, it's less or equal than delta times the probability that t is less or equal than n plus delta. And therefore, if I push to the left-hand side this first term, what I get is that the probability that t is less or equal than n, that this is bounded by delta divided by 1 minus delta, as we wanted to prove, because we have seen that this event corresponds to that event. So we have indeed that this probability is bounded by delta divided by 1 minus delta, as we claimed. And with this, we complete the proof of this lecture.